And we are live. James, stop. Hold on. We have some technical difficulty. I don't see sound. Only my sound going through. Zoom not transmitting the sound. They can't. Oh, they can't even see you anymore. What happened with Zoom?
Yeah.
But yeah, difference so far.
Wukash just looks.
Go back to the UK. A few days later, I'll be moving, and so I'll have moved, but it will look the same. Yeah.
Oh, I didn't know you were relocating within the same unit, or sorry, not the same.
Yes.
Within the same building.
Yeah. It's very
Changing into the same building.
Yeah.
Okay.
It's a nice area. It's like next to some psychopaths. There's a supermarket nearby, and
there's some psychopaths.
Cycle.
Oh yeah, trails.
yeah. Just like, but also I kind of grew attached to these foxes that live nearby, and I feed them occasionally.
Yeah.
So I want to stay there. And yeah.
Nice.
All right.
Okay. Something. Did it work?
It should work. We are live. Go. Continue.
We're live. Greetings, everyone. Welcome to another Wolfram Institute live science stream. Apologies for the technical difficulties. Anyway, so we are going to discuss a new research project during this stream, and that new research project is occasioned by the onboarding of a new research fellow, Richard Assar. Now, you might have seen Richard on a previous stream or two, our community forum last week, for instance, as well as perhaps other streams, in particular the ones with Carlos on subaxiomatic foundations of mathematics. But we haven't yet had a live stream dedicated to the project that Richard is doing. So I'll provide some motivation, context, and then we'll begin speaking with Richard about the work that he's doing. Okay, so well, for those of you who have been following either the work that Ruliad or Rulial space, so this sort of and somewhat provisional entity or object, it's described somewhat qualitatively, though some kind of simple example defined, and we don't really have any way of working with it concretely at the moment. So Richard is going to be helping us with that. If you're familiar with what I was just saying, let me provide a brief kind of introduction, though I have to think carefully about how exactly I want to set it up. I mean, the Ruliad has been described in the past as the kind of space of all possible computations. You know, we're familiar with running, in particular, kind of formal systems such as cellular automata or string write systems or Turing machines or register machines or etc. We can also create multi-way systems of these where you have different paths, different evaluation paths that are shown optically. You can take multiple Turing machine rules and produce multi-way systems that actually capture the behavior answerable to these rules put together into a common rule set. You can also do that with cellular automata, for instance, where you take rule 30 and rule 31 and rule 32, like a multi-way cellular automata out of that. The idea for the rule-add is in some sense you can spatialize all compute together. Now, there are many conceptual ambiguities and problems that need to be addressed if we're going to do any real work with the rule. I mean, for instance, sometimes the rule-add is described as a space of all possible rules, but a rule and its computation are quite different things. You know, if you were to spatialize just rules in their own right, what would that even look like? A rule doesn't even have any graphical extent. I mean, I guess you could take an expression tree or something for a rule, but that's not really what's even in mind. So the rule-add is not really a space of all possible rules. It's more of a space of all possible computation. So with Richard joining us, I've been trying to think about ways in which we could, usefully create some sort of an object that spatializes or otherwise parameterizes computations, and in part inspired by constructivist mathematics that we're also doing. I posed the question, can we create a space that parameterizes algorithmic constructors by the computations that ensue from them? And more specifically, I thought we could create something like a moduli space of causal graphs. So let me break down what I mean. A moduli space is a kind of space that is often used in fields of mathematics such as algebraic geometry to parameterize given objects, where an isomorphism class of that object will be a particular point in the space. So the idea of a moduli space of causal graphs is, okay, so sorry, I said what a moduli space is. I should say something about what a causal graph is. So, okay, so, suppose that we're going to execute some arbitrary computation. We have some algorithm, we have some rule. Often when we're doing rewrites, we refer to the algorithm as just a particular rule. Left-hand side, right-hand side. Maybe it's a two-way rule, and you can go either way. So again, if you find something that matches on the right-hand side, you could go back to the left-hand side. So you're given some initial data structure. That initial data structure could be quite simple. It could be a short string, it could be a short hypergraph, et cetera, et cetera. You have some initial condition, you have some rule. I like to view that as a constructor, a kind of an initial, a kind of a pair of some rule and some initial condition. It's unfair, I think, or misleading to just go by the rule alone, because you can have radical dependence on the initial condition. Okay, so you have some pair of a rule and an initial condition, and then you begin computing, and you can look at the computation in one of two ways. Okay, you can look at it in many ways, but I'm gonna distill two different ways in which you can look at the computation. On the one hand, you can ask what happens to the underlying data structure as it's being rewritten. So you start with some initial data structure, you start with some initial condition, and you perform rewriting on it. So you can ask, well, what happens to these? You could view those in terms of states. You could call them states. You could call them tokens, and you could ask what happens to them as they evolve. But you can also do something different, which I think, with time, largely under the influence of Nick, I've come to prefer this view, because I think that it captures computation in a more direct and in some ways a more abstract fashion, and that is to somewhat disregard to some extent the underlying data structure and to just look at the actual operations involved in the computation itself. And we can view these operations or these executions like actually performing the rewrite, the Turing machine actually, operating. We can view these things as events. Now, the term event has some physics. It invokes some ideas for physics. We'll just refer to them as events, but in a kind of an abstract computational sense, they're basically computational operations. Now, we call these things causal graphs because there are dependencies between computational operations. There are some operations where you had to have done some, preceding operations and anterior operations before you can do the next one. And so you can actually make graphical the particular operations and the causal relationship between them, the operations of particular vertices in this graph, and the directed edges are the causal dependencies. We refer to these things as causal graphs. So when we're considering kind of moduli spaces, or perhaps in the future also classifying spaces, this is something that Jonathan has often brought up. Jonathan has kind of asked, see this as kind of a topos for computations. I think Jonathan has a point there. I'm personally interested in both classifying spaces and the underlying data structure. And I say this with an asterisk or a proviso